All right, guys. Thank you for coming. This is another session of the CMU, or the Carnegie Mellon Vaccination Database Series. We are happy today to have Gian Merlino. He is the CTO and co-founder of Imply, which is the main startup backing Apache Druid. He's been at Yahoo. He was at MetaMarkets before Imply, and he has a computer science degree from Caltech, which is a small program. So there's not many of you guys out there. So that's awesome. And so, as always, please, if you have any questions for Gian as he's talking, please unmute yourself, say who you are and where you're coming from. And again, we want this to be a conversation, so feel free to interrupt at any time. Okay, Gian, the floor is yours. Go for it. Thank you for being here.
All right, great. Yeah, definitely. Thanks for having me. So today I'll be talking about Apache Druid, and I'll be talking about its storage and query engine, and a little bit of how the system all comes together. Let's see. Who am I? I'm Gian Merlino. Thanks for the intro. I'm a committer and project PMC chair at Apache Druid, and I'm also co-founder at Imply. If any of you are looking for jobs after you're done learning about databases and you want to work on databases professionally, we are hiring. Come talk to me. All right, what are we talking about today? So first off, I'll do a brief introduction on Apache Druid. What is it for those of you that are not familiar with it? I'll talk about the core concept of Druid, which is a segment. It's the core data concept, core data format that everything revolves around. Talk a bit about how data servers work, how a cluster comes together. Druid is a distributed system, and then zoom back in from the 10,000-foot view of a cluster into the smaller view of the segment file format and how an individual query gets executed. So we'll talk about all levels of the system. It's a complex distributed system with a lot of different zoom levels. So I think it's kind of interesting to take a little bit of a look at each one of them. So first off, what is Druid? Druid is a powerful query engine. We like to think of Druid as this rocket ship that goes really fast, but that's when we are really just full of ourselves and have our head in the clouds. What Druid really is a fancy calculator. And it's a system for adding things up really, really quickly, counting things, taking mins, maxes, averages. It's a fancy calculator, but people want a fancy calculator on huge amounts of data. Being able to do that really efficiently is good. Druid powers OLAP apps. This is the kind of app that you want a big fancy calculator for. OLAP is online analytical processing, just a term for doing aggregations, filtering, that kind of thing. Mostly very read-heavy workloads that hit the entire data set or large slices of it. You don't tend to be hitting one row at a time. You tend to be hitting large chunks of the data set. And on the right side, it tends to be more insert-based than update-based. So lots and lots of inserts, lots of reads of big chunks of the data set. Tends to be useful for interactive analytic applications where you want to do visualizations, like the one you see here. That's one that we make at Imply called Pivot. Druid also speaks SQL, which is a standard language for doing this kind of stuff, and people build their own apps on top of it. Druid's been around for a while. It enjoys nice use out in the wild. Druid's used at Netflix for analyzing user experience, used at Twitter MoPub for analyzing data related to online advertising and mobile publishing, use at Salesforce for understanding what their users are doing, use at Airbnb for analytics on the mobile app. So use all kinds of people that have these really big scale problems for delivering analytical applications. Some numbers from Imply customers. So at Imply, we are one of the big sponsors of Druid. We have a lot of engineers working on it full time. We're certainly not the only company behind it, but we're one of the big ones. And some numbers from Imply customers, petabytes of data under management, thousands of daily active users, millions of rows per second ingested, and very fast query times. All this with 90 percentile query times less than a second, and even 99 percentile query times less than 2 seconds over the last month or so when I pulled these this morning. So we're running it at really high scale at really high speed, and that's what Druid is designed for. And I don't want to.
For the queries that exceed your 99th percentile, what are they doing that calls them to get crushed? Is it just they read a lot of data, or is it like they do crazy joins? Like what is it? Like what is that? Yeah, go ahead.
So it's a long tail of a variety of stuff. So some of them are doing crazy joins, some of them are reading more data than normal. A lot of them do read a lot of data. So even the 99th percentile, even the fast ones generally do read a lot of data. The ones on the slower end, it tends to be a mix of doing more complicated stuff than is typical. So like a typical query, people really do want pretty simple stuff. Like I over an incredibly large amount of data, I want relatively simple statistics. I want to know what's the median of this, the average of this, that kind of thing. Sometimes we want to know something more fancy that takes more time to compute on a per row basis, and that can take longer. And sometimes people want to query more data than typical. So maybe typically you'll be looking at a year of data, but every once in a while you want to do a query over 10 years of data.
Okay, all right, thank you.
Okay, so I didn't want to talk too much about this stuff because this is a internals talk. I just wanted to motivate y'all for why you would want to listen to the next 45 minutes. So let's get into the details. Inside Apache Druid. I hope that some of you are familiar with this video, The Powers of 10. It came out in the 70s. I think I first saw it in my childhood at a science museum, and it captivated my imagination. It's a pretty cool video. It's about 7 minutes long. If you haven't seen it, check it out on YouTube. It is a video of going all the way, zooming all the way out from this gentleman at a picnic, all the way out to the bounds of the known universe, and then zooming all the way in to a proton in a molecule inside one of his cells. And I want to do a similar thing with Druid. I want to start from sort of a mid-level zoom, and then zoom all the way out, and then zoom all the way in. So let's go on that journey. We'll start off with a segment. The Druid segment is, like I said, the core concept that everything revolves around. It's got about 1 million rows in it, so we're at 10 to the 6 rows. And this is sort of the mid-level zoom level for Druid. It's a heavily optimized storage format. It's a columnar format like every other analytical database out there. It's, with Druid, you're going to get the greatest hits of columnar databases. New segments are created continuously as data is ingested. So roughly every million rows, every 1 to 10 million rows of new data coming in, we're going to get a new segment generated. So a cluster with a lot of data could have hundreds of thousands or millions or even tens of millions of these segments. They're immutable once created, but they can be dropped, replaced, or combined. And we call combining compaction. And if you're dropping them, that's like deleting data. And if you're replacing them, that might be what we would do that if you issued an update command. And generally 1 to 5 million rows each. They have a life cycle. So this is a little depiction of the life cycle of a single segment. We in Druid have 2 node types. One's called the indexer and one's called the historical that interact with these segments directly. The indexer creates them. So it reads data, it reads streaming data, batch data coming in. It generates segments. It pushes them to it does that. It pushes them to what we call deep storage. Deep storage is, it's going to be something like S3 or Google Storage or HDFS. It's some kind of distributed storage. It's a Druid occupies, and this talk isn't really about the separation of storage and compute, but suffice to say that in the sort of 10 years ago we had Hadoop coming out saying that we get all of our speed from co-locating the data and the compute. And now we have the newfangled cloud data warehouses that are saying that we get all of our versatility from separating storage and compute. And these are both true. It's faster to combine them and it's more versatile to separate them. And Druid occupies, I think, a really interesting point on that spectrum that we actually get a little bit of benefits of both sides of it. But this talk isn't about that. I just wanted to mention it. Anyway, we push things to deep storage. And then other servers pull from deep storage. So deep storage is sort of all data we've ever ingested is going to be on deep storage. It is going to be pulled, loaded locally by the historical servers. And they do this as a preload before a query actually happens. So this is what I mean by the sort of interesting space. When you have systems that completely separate storage and compute, generally things are pulled from storage on demand during a query. They might be cached, but they're generally pulled on demand. When you have systems that co-locate fully storage and compute, you tend to have data coming into a server and then stays on that server for the long term. In Druid, the hybrid model we have here is the data is not, there's no strong affinity of data to a specific server. So these segment files can float from server to server. When they're ingested, they end up generally on a different server than the one they came in on. They can be repartitioned, shuffled, all these kinds of things that you would expect from a system where they're separated, where storage and computer separated. But for the one difference that we do pull things from deep storage onto the data servers before they're queried. So it's a prefetch rather than a cache. And that's for performance reasons.
So I think Hamid, you have a question, unmute yourself. He's in the chat, but it's me from IBM. Where is he in the chat? I can.
Yeah, hi Andy, thank you.
Hey, what's up, man? Go for it.
Yeah, so one question is that when you read the data from local, so either memory or NVMe, what is the bandwidth of your read, the storage read? Is it like 2 GB per second or it is 10 GB per second?
Yeah, so we're reading.
Go ahead, sorry, go.
No, what were we gonna say, Andy?
I was Hamid. Are you talking about like the Imply hosted version of Druid, right? Because it obviously depends on the hardware.
Yeah, I mean, you got say NVMe. Suppose you have a reasonable, amount of the CPUs, like go extra large version from AWS. So I want to see that you are.
I actually don't know. I tend to think of it more in terms of rows per second than in terms of bytes per second. And those are the numbers I have on the top of my head. So in terms of rows per second, for a simple query, you might get 100 million rows per second per processor. And for a more complex one, you might get 1 to 10 million rows per second per processor.
Yeah, okay. So let me ask you differently. What is the bottleneck? Is that the CPU or is the storage? Not the backend of storage, local NVMe or even memory.
Yeah, good question. It depends on how your ratios of your storage hierarchy. So typically people with what we call hot data will have a ratio of memory to disk that is very high and a ratio of CPU to memory that is relatively low. And in that case, people tend to be constrained by CPU and memory bandwidth. And which one they're constrained by depends on how good locality is on the data. If locality is bad, they'll be constrained by memory bandwidth. If it's good, they'll be constrained by CPU.
Okay, so you say that if the data is in memory, you can actually keep up with the memory speed, which is a very high speed.
Yeah, and we'll talk about that in a little bit when we talk about how the compression works, but we prioritize compression and encodings that can be decoded very rapidly. Okay. So the idea is to be able to, we basically optimize everything for the case where locality is good and where you're CPU constrained. And so we prioritize things that let the CPU fly as fast as it can, but we do tend to be CPU constrained.
Okay, so my other question was at some point probably going to answer it, that compare this your offering with the Cloudera Druid.
So Hamid, let's do that one at the end, okay?
At the end, not now. Sure.
Not now.
Okay.
Yes. Okay. All right.
Okay.
Gian,
cool.
Go for it.
Sure. So let's see. Okay. So what I was saying is that there's this interesting spot on the storage compute combination or deaggregation spectrum, one of the things that happens here is what we call balancing. So, I mentioned that there is a affinity of data of segments to servers, but the affinity is not as strong as a system where storage and compute are completely linked, but it's not as loose as one where they're completely separate. And so in a completely separate system, data would get pulled on demand. That doesn't happen in Druid. In Druid, we have a process called balancing in order to move data from one server to the other as things make sense. And in that balancing process, what happens first, the step 5 in the segment lifecycle is another historical, a different one loads it, and then the original one will potentially drop it. And balancing happens as new data is loaded in an effort to keep load relatively consistent across the data servers.
It is just a cache though, right? Because like the storage of record is the deep storage, right? You're balancing to decide, okay, drop cache here and pull cache up here.
Yeah, we actually in the code we actually call it a cache, and it is a cache. I find that usually it's sometimes when I call the cache and talking to people, people think that it's a cache that's populated on demand. It's a cache that's populated ahead of time instead of on demand.
Sure. Okay. But I mean, I wouldn't call it. It's not hybrid shared nothing shared everything, right? It's or shared nothing shared disk, right? It's shared disk just with smarter cache.
Yeah, that's sort of how I think about it.
Okay, that's fine.
And the caches are completely local, and we never query from the. If you can think of deep storage as a shared disk, that's never involved in the query path, which is the main difference between what Druid would do and what something like Presto or Hive would do. Is they might do some caching, but they would also involve the storage layer in the query path, which Druid doesn't.
Got it. Okay.
Okay, so that's the 10 to the 6th level, 1 million rows. Let's go up one zoom level. Let's go to 10 to the, oh my God, I got the wrong thing here. Okay, fix it in post. This should be 10 to the 10, not 10 to the 13. Inside a data server, 10 to the 10 rows, not 10 to the 13. That would be a really awesome data server. 10 to the 10 rows on a data server. Let's talk about the goals of a data server, of one data server. So there's the two goals revolve mostly around how we want to deal with CPU and memory, two sets of goals. So for CPU, one goal is we want to be able to harness all available CPUs for a single query, which means everything we do has to be multi-threaded. And another goal is we want to balance CPU usage across concurrent queries in some kind of, optimally in scare quotes. Who knows what optimal means, but we'll define what we think optimal means in a little bit. And then on the memory side, we want to be able to take advantage of high memory hardware. So if you do have enough memory to hold your entire data set, we want to take advantage of that in an optimal way. We also want to be able to fall back to disk when memory is insufficient. For the kinds of applications people build on Druid, it's generally the most important part of the application is how does it perform on this hot data, which is generally 50 to 80% memory. So we spend a lot of time optimizing for that case where most of your data is in memory, maybe not all of it, but most of it. And then there tends to be a fraction of the use case that is on colder data. And this might be something that's like, maybe the hot data is the past year, like I was saying, and the colder data is the 9 years before that. Or it could be a table by table basis. It could be certain tables are hot and certain tables are cold. However it is, the typical application built on Druid is mostly hot and some cold. And so we want to be able to handle both of those use cases in one system. All right, now the legend is back to the correct 10 to 10 rows. So let's look inside a data server schematically. So there's these sorts of 3 layers in terms of how we think about what's going on inside a data server. On the bottom layer, we have all the segments on that data server. It could be maxes out at a couple 100,000 or so. Memory mapped disk. So we, like a lot of other systems invented around the time Druid was and modern systems today, we rely heavily on memory mapping. It works really well. It works really well with SSDs, which are pretty popular these days. So like a lot of modern databases, especially a lot of modern analytic databases, Druid's meant to run on SSD-backed systems. And so we have all the segments lying on disk. We memory map all of them. And we let the OS figure out what's going to be in memory and what's not. So we don't actually have code in Druid to figure that out. We just we allow the OS to figure it out. Above that layer, we have the processing thread pool. There's 1 thread per CPU. And then we have the processing memory pool. And there's a certain amount of memory we'd allocate per CPU as well, generally on the order of ½ gigabyte to a gigabyte or so. And then the top layer, we have some per query resources. So the bottom layer is all memory math files. The middle layer is resources that are per CPU. And the top layer is resources that are per query. And let's talk a little bit about how these resources get managed.
Quickly, for the memory map files, are you guys doing likemadvise or like giving the hints to the OS about like what the vfetch and things like that? Or are you just letting the OS blindly do whatever it wants?
We're doing the second one.
Okay.
We might start doing madvise at some point. I think some folks have done some experiments in the open source for Druid, but none of them made it into mainline.
Okay, all right. And then for your thread pool, is that just all bespoke code, or are you relying on like there's the Intel thread building blocks. There's a couple other like scheduler stuff that's out there. You use any of those?
Yeah. So Druid's written in Java. We are using
Yeah.
mostly the standard thread pool in Java util concurrent with one change that we added to for prioritization purposes, which I could talk a little bit about in a couple of slides. But we've changed how it prioritizes tasks that are queued up to be processed. The rest of it works the same way as the basic Java one.
Okay, thank you.
So in terms of the resources of the server, a lot of what we've done in the server to manage these resources is based around prioritization. And the reason that's important is because the base design of the system, if you look at the processing thread pool, the memory map disk, the basic design of those layers of the system achieves the first goal I mentioned. It achieves the goal of enabling a single query to use every CPU if it wants to. Because we have a lot of segments. Every CPU, there's many more segments than CPUs. You know, a server might have 100 CPUs and 100,000 segments. So there's many more segments than CPUs. So if you split up the segments to the CPUs, then you get good multi-threading right there. The issues come in, or the issue in this design comes in when you have concurrent queries and you want to balance resources between them in some fair or optimal way. I think about it more in terms of more in terms of optimal than fair, because you don't really want to be fair necessarily in a system like this. You want to do something that the user is going to expect. And that, to that effect, we built a prioritization system inside Druid. And the idea is that most people have a variety of workloads they want to put on a system like this. And some of those workloads, they expect to be fast, they expect to be interactive, and some they don't. And what we want to make sure of with the prioritization system is that the workloads that people expect to be interactive remain interactive, even when the system is under a high load. Of course, that's not possible in the general sense without auto-scaling, which is something that in Apache Druid doesn't exist. People on top of the Druid have built auto-scaling type stuff, but I won't be talking about that today. In terms of the base system, that does not automatically scale in the open source. The ability to meet these expectations is mostly built around prioritization. So prioritization, here we have 3 queries. 2 of them are outlined in orange and one's outlined in blue. The orange ones are high priority and the blue one is low priority. The way that the lower levels work is that if we have a bunch of queries in the system, some at higher priority, some at lower priority, the higher priority ones get priority over everything at the lower levels. They get priority over all the CPUs and all the memory pool. So they could, if they wanted to, take all the resources away from the lower priority ones, which is generally what people expect to happen. Generally, people expect lower priority work to sort of exist in the gaps between high priority work. And in practice, this takes advantage of the property that the high priority work tends to be pretty spiky. It tends to be human driven by people clicking around an analytical application. It doesn't tend to be space filling. It doesn't tend to fill all the available computation time the system has. And so when there is high priority work happening in that instance, we do it. And when there's no high priority work happening, then we fill the space with lower priority work that may be around. This extends down to the lower system because the segments are all loaded. They're basically accessed as needed. As these processing threads access areas of the segment, the OS will keep them paged in, or a page emitter keep them paged in. And this is also tends to be helpful because it tends to be that the higher priority work and the lower priority work don't always want to access the same segments. They tend to want to access different tables or different time ranges or that kind of thing. Okay, so that's one data server. Let's go up one more level. And talk about how a cluster comes together. So this is, now we're finally really at 10 to the 13. This is 10 trillion rows. This is about as big as one cluster is going to be able to get with the design that we have in Apache Druid today. Above this amount of rows, you might want to make 2 clusters. Anyway, so there's a query server called the broker. Like I said, Druid speaks SQL. The broker is actually the piece that does speak SQL, and it translates the SQL query into what we call a native Druid query that every other server in the cluster can understand. So there's this one server type that speaks SQL, and everybody else understands a much lower level native language that's more operator It's more physical operator oriented and less logical than SQL is. And we call this process query fan out, because a query starts in the broker, fans out to every data server that has data relevant to that query, and then fans back into the broker. Okay, so now that's as far up as we go. And now I want to go down. So let's go back to the segments, and then we'll start zooming into the segment and talking about how individual segments are structured and how queries execute on those individual segments. So back to segments, back to these 1 million row data files. This is an example segment. This one has 8 rows in it, not 1 million, but that's only because I can't put 1 million rows on a slide. So just pretend. So there's 8 rows in this segment. This segment has 5 columns: time, artist, city, price, and count. This is sort of I guess a pre-COVID data set of ticket sales. So there's 3 different artists and 3 different cities, and this data set is how many tickets were sold for each artist in each city and what the total price was. Okay, so I want to look at a few columns, column by column. Like I said, this Druid is a columnar database, like all columnar databases, we store each column separately, and each one has its own kind of encoding, its own kind of compression, and is in terms of locality, is all stored together in the same place on disk, and so it can all be loaded into memory together and all be transferred to the CPU together. So these are all the timestamps that we've stored. They're all the same in this example, likely because in this example, when we ingested it, we chose to truncate timestamps to the hour, or truncate them to the day, or something like that. So they're all the same here. These are going to be stored probably with table encoding, which is one of the ways we can encode integers. We do it for integer columns that are low cardinality. So it'll likely be only a bit per 1 bit per column. Oh, sorry, 1 bit per row. The next column is artist, and the artist column is a string. It has 3 sections. It's got a data section. There's also 8 values here. There are 8 values in the same order as the other 8 values. So every column has 8 values. They're all row 0, row 1, row 2, up to row 7. So there's this is in the artist column. The first 3 rows are Justin. The next 2 are Kesha, and the next 3 are Miley. Really very dated musical references, but what can you do? There's a dictionary section. So all of our string columns are dictionary encoded, which is useful. And I'll talk about that a bit later about why it's especially useful. And then we have an index for each of these columns, and the indexes are bitmaps. We use either concise or roaring for the bitmaps. Generally these days we prefer roaring. That's the default today. One of the nice things about these is they can be stored compressed, and they can be combined, they can be intersectioned and unioned in their compressed form, which is really cool. Then finally, we have all the other columns. All the other columns are, like I said, every one is going to have 8 values, and they're all going to be stored the same order. So if you want to retrieve row 3, you would read the 3rd value out of every one of these columns. Obviously, that's not a very efficient way to retrieve a single row. Which is why these kinds of layouts are used for databases where people want to do aggregates over big chunks of data, as opposed to where people want to retrieve single data points.
So when data shows up in the indexer and you're building this, right? Like you have to wait till the segment is full, then you run your pass on and decide how to build the dictionary, right? Because you can't know all possible.
Yeah, that's true.
You see ahead of time. Before you sort of freeze the data in the segment in compressed form, is it accessible through like the execution engine for queries?
It is accessible. It's in a row store then that is in memory and doesn't use this format at all. It's a pretty common technique used in columnar databases to have a row store that flushes to a column store.
Yep.
If
you have
yes.
Question. If you have the bitmap indexes, why do you need the data segment? Can you reconstruct the data you need from the index?
You can, but storing the same data in 2 different ways is useful because we might want to do different things with it. Generally, if I'll go through an example query where this will hopefully be illuminated, but in general, if you're going to be filtering on something, it's faster to use the index. And if you're going to be grouping on something, then it's faster to scan the data section. Okay, so that's a really good segue into this next slide, which is let's do an example query. Let's go through how Druid would do this query on this one segment basis. So in this SQL query, we are going to group by city. We are going to add up all the prices, and we're going to for artist equals Justin. So we just want to see for Justin, what are all the cities that people bought tickets in, and what was the total price for those tickets. Okay, so the first thing we're going to do is we are going to resolve the where clause. And we're going to do that by looking at the dictionary first. So we want to figure out what is the dictionary code for Justin. And we store the dictionary sorted. So J, K, M, these are in lexicographic order. And we can do a binary search through the dictionary to find any particular value. It doesn't really matter much here. There's only 3 values. A scan would be pretty quick as well. But in situations where there's 10,000, 100,000, million values in a segment, then the binary search really helps us out. So we're gonna binary search through the dictionary. We're gonna see that Justin is 0. And then we're gonna head on over to the index and get the 0th entry. The index is the same cardinality as the dictionary, and the values are in the same order. So the 0th thing in the index is the bitmap for Justin, and you see the first 3 positions. The first 3 bit positions are 1s here, and the rest are 0, signifying that this particular column has Justin in the first 3 rows, and then the other rows it doesn't. Next, what we're going to do is we are going to head on over to the city and price columns to do the group by, and so we're gonna read them both at the same time. And here we're going to use a data section instead of the index because we have the row numbers that we want to read. We know we want to read rows 0, 1, and 2, and the fastest way to read 0, 1, and 2 is to look at the data section. So we go to the data section, we see that the first one is 2, and then the price fed is 1800. Then we see 1 and 2912, and then 2 and 1953. And we add all these up into a scratch space. That's scratch space that we've allocated out of the processing memory pool from a few slides ago. There's a few different ways we might do it. We might use a hash table here. We might use an array here. We might use a heap here, depending on whether we're pushing down the limit, depending on whether we know the cardinality to be large or small. In this case, because the cardinality is small, there's only 3 values of city, we're going to use an array. So this is actually just going to be a long array, so a 64-bit int array with 3 elements, 0, 1, and 2. 0 is going to have nothing in it. 1 will have 2912, and 2 will have 3753. Then we're going to go to the dictionary after reading through the column. After reading through both columns, we're going to go to the dictionary and replace all of the dictionary codes with the names. And we do this on a per segment basis because every segment has a different dictionary. And so in order to merge results from different segments, we have to, at this point, after we've aggregated the data for one segment, we have to then replace it with a dictionary with the name. So now we have LE and SF. We ditch the null. We ditch 0. We don't look it up in the dictionary because it didn't exist. It was not found. And then we have the final result for this segment, which we will then go on to combine with the results from other segments and then return it to the broker. And this I think illustrates the power of this particular format. The awesome thing here is that in order to do the filter, we never had to read the data section of the artist column. We only read a dictionary. We did a binary search through it. We did a single random access into the index. We didn't even do a search in the index. And then to do the aggregation, we knew which rows we had to read. We knew we had to read the first 3. We did it using an array instead of a hash table, so a much smaller per row cost. And then after the aggregation was done, then we replaced the IDs with names from the dictionary. We only had to do that one time per unique ID. We didn't have to do it once per row, which in this example does not matter that much because there's only 3 rows and 2 IDs, but a more realistic scenario would have millions of rows and maybe hundreds of IDs. So there's a big boost there. Okay, let's see. So that's what I wanted to say about that. And then I want to move on a little bit to one more zoom level down, blocks within segments. So now that was 10 to the 6, that was one segment. Now we're 10 to the 3, 1,000 rows. Each of these segments is split up into blocks. of not exactly 1,000 rows, but of that order of magnitude. And I'll talk a little bit about why we do that and why that matters. So let's think about one column within that segment. This is that artist column. And in this artist column, we had a data section that had 8 rows in it. That 8's not really enough for talking about this concept. So let's pretend it had 16 in it. So let's pretend it had 16. I made up a new one. And let's pretend that each of these blocks is 4 rows instead of 1,000. So here's a segment that that has 4 blocks in it. Each block is 4 rows. In reality, there would be many more blocks. Each block would be about 1,000 rows, but bear with me. And the first 3 rows are Justin, and then there's some Keshas, then some Mileys, and there's some more stuff. Then there's another Kesha, another Justin, another Miley, another Kesha, and so on and so on. So data layout is really powerful, and it helps to think about these blocks when you think about data layout. Each of these blocks is individually compressed. And because each of these blocks is individually compressed, typically we use LZ4 for this. When each of these blocks is decompressed, we must decompress the entire block because LZ4 is not an algorithm that enables random access into a compressed payload. So what we do is we read a block containing about 1,000 rows, we decompress that block, and then we're able to operate on any of those 1,000 rows relatively cheaply because the block's already been decompressed. The idea here is, let's say we're filtering on artist. Go back a slide. Let's say we're filtering on artist. Let's say we're filtering on artist equals, let's say Kesha. So if we're doing that, then we have to read 3 of these blocks. We have to read 3 blocks because the first 3 blocks have 1s in them. The last one doesn't, so we don't have to read it. But we have to read a block if it has even 1 row with a particular value in it. So we have to read these 3. That's 3 blocks that need to be decompressed. And again, we have to pay that cost to transfer those blocks from disk to memory, from memory to CPU, to run LZ4 on it. And then we can decode the 1 row that we want to read. But that's a lot of cost to pay to read just 1 row. So if we sort, we can address this by sorting. We can address it by sorting on artist. Of course, we can't sort on every column at the same time. That doesn't really make sense. So typically people choose to sort on a column that is something they're commonly going to be filtering on or commonly grouping on. So let's say that in this data set, we're going to, let's say we're Ticketmaster and we're almost always filtering on artist. So if we're almost always filtering on artist, then we might want to sort based on the artist. And that way, here now we're filtering on any artist. We never have to read more than 2 blocks because all the Justins are clustered, all the Keshas are clustered, and all the Mileys are clustered. And clustering things this way minimizes the number of blocks to read, gives us better data locality, and speeds things up quite a bit. I have a little example of how that, of a real world example where that actually helped a lot. So I mentioned Druid is in Java, written in Java. This is what we call a flame graph. This is created with a tool called SJK. I think it stands for Swiss Java Knife. Anyway, it's a cool tool that this is a profile of a query that was running. In this situation, this is a query that was running on a time series data set with a bunch of sensors, a bunch of facilities. And you can see that 90+% of the time being spent here, the tops of all these stacks in the flame graph is LZ4 decompressed. So we're spending a ton of time decompressing things and very little time doing anything else. And this is a pretty common thing to see if you have a data set with poor data locality and you're filtering into a small slice of it, which is the case here. We had a data set of a bunch of sensor data from a bunch of different facilities, industrial facilities. And the particular data set, the application wanted to filter onto specific sensors and specific machines and specific facilities. And so it was grabbing a point out of this block, a point out of this block, a point out of this block, and you get a flame graph like this. When we change it to cluster the data by machine, so all the sensors for the same machine and the same facility together in the same segments in the same blocks, the overall CPU time for a query went down by 8x. So the queries got 8x faster, or equivalently, that could be the same speed on an 8 times smaller hardware footprint. And you can see that the LZ4 decompression part of this flame graph is, it's not, I don't know, eyeballing, it's maybe 15, 20%, much smaller than 90+%. And so this is a much more healthy looking flame graph where we're not spending all of our time decompressing blocks just to retrieve 1 or 2 points out of them. So let's see. Finally, I wanted to talk about one single row. So going down to 10 to the 0 rows, one row. On one row, we're doing type-specific compression. So for strings, we're doing dictionary encoding. For integers, we're doing potentially table encoding, potentially delta encoding being encoding differences from a base value. Table encoding, meaning there's a small number of unique integers, and we are going to give each one dictionary code. So we could do dictionary encoding for integers as well as strings. And then data-dependent packing. And what I mean by that is we're packing into a certain number of bits based on the range of data encountered in that segment. So if in a given segment we encounter data that spans a range that could be packed into 6 bits, then we'll store 6 bits per row. For indexes, we're using roaring bitmaps, like I mentioned. So there's type-specific compression being used there. And for layout, the value of each value of a row is being spread across all the relevant columns. So we sort of explode each row, which increases the cost to retrieve a single row by quite a bit. But that's okay because we don't really need to retrieve single rows. That's not really what we're trying to optimize for. We're trying to optimize for scanning large chunks of data. And this exploded storage format is really useful for that because each column can be loaded separately into memory. And then rows that are likely to be queried together can be clustered together within those columns, leading to really good, I guess, flow of data from disk to memory to CPU.
Sorry, what is table encoding again?
Table encoding is, it's the same as dictionary encoding, but at least in Druid parlance, when we do it with string, we call it dictionary encoding. We do it with the integer, we call it table encoding.
Okay, okay, but it literally is like, I repeat the same digit over and over again, so I'll store it in you know, a mapping from that with a code to what the actual real value was.
Yeah, it's like in this column, it's designed for, it's most useful for integer columns where the integers are IDs of some kind. So you know, maybe you have a customer column and a customer ID. There's 100 customers, and you know, maybe the numbers are really wacky. You know, maybe you give them all like random numbers. We'll crunch them down to 0 to 100.
I understand. Okay, yeah. And then your data dependent packing.
Yeah.
That's just bit packing.
Yeah, exactly.
Okay.
Yeah. Bit packing for on the scope of one column. So whatever the spread of data is for one column determines the number of bits for that column. Okay, so that's what I had prepared. And if you want to stay in touch, if you're interested, follow us on Twitter, which we are at. Check out druid.apache.org, the project website. And again, if you are hiring an Imply, imply.io/careers. Thank you, and I think we have some time for questions.
Yes, awesome. So I will applaud on behalf of everyone else. So I always have questions. So let's open up to the audience first. So I know Hamid has a question, but there's somebody else in the chat. You want to unmute themselves? I can unmute them. Force them to talk. EYAL, Yerman. Go for it.
Hey, Jen. So I just wanted to see if you can talk a little bit about how the columnar architecture represents itself in the data storage. Where exactly is the separation to different columns? Is it in the file? Is it in the block level, etc., etc.?
Yeah, so good question. If you think about each segment as being its own miniature database, which I think is a good way to think about it. I mean, I guess technically if you had, it's a good way to think about it because if you did only have a few million rows to query, then you would only need one segment, and that one segment would be the entire database. So if you want to think about it that way, then it's all stored in a single file. And in that single file, every column is laid out end to end, and then they're all stretched out in a line. So the first column might occupy bytes 0 through 5 megabytes, and then 5 megabytes through 8 megabytes might be the next column, and then 8 through 12 be the third column, and so on and so forth.
Question? If you have a really, oh, sorry.
Oh, sorry, Morgan, go for it.
Hi, Gian. My question was, I know you're talking about dictionary encoding for the string columns, right? I know it makes sense when the cardinality is very low. What if my cardinality of the particular column is very high? Even in that case, are you guys going to do the same dictionary encoding, or what are the cost implications in that aspect?
Yeah, that's a good question. We are going to do dictionary encoding in that case as well. And I guess the follow-up question is that a good idea?
Yes.
And I guess it depends. What are the alternatives? I guess the main alternative is to store the high cardinality string in line in the segment. Because if you think about the way the dictionary works, the dictionary is sort of like internally, it's sort of like a pointer. So we have dictionary code 0 is a pointer to a location in the dictionary that has that string, and then 1 is a pointer to a different location, 2 is a pointer to a different location. And you could store those things instead of pointers, you could store them inline. And storing them inline has the advantage of having better locality than storing them as pointers. So it might be a good idea to store them inline. It might be an especially good idea to store them inline if they are always a certain length. And so maybe if your high cardinality strings are UUIDs, well, I guess that's a bad example because those are integers really. But if there's something else that's a fixed length, it might make even more sense to store them inline. It might be a good future improvement to Apache Druid.
Okay.
I think just in conclusion, I think what we do now is, I think it works, but the main downside is you're not getting a ton of benefit from it, and you might get better locality if you store them a different way.
Okay, we'll do Ben next, and then Aaron after this.
If you have a really large data set, which has a bunch of segments, and you want to do a query that only touches a handful of rows, do you get issues with having to fan out to do a random lookup on the index of every single segment?
So let's see, there's two scenarios there. One scenario is where you are filtering on something that is a way that you've partitioned or clustered the data. Because I talked about how clustering is useful within a segment, but clustering is also useful across segments because data can be clustered into segments. And if thinking back to this artist example, this ticket sales example, if you partition your data across segments based on artist, and then they're filtering on artist, not only will the data be clustered within the segment, it'll also be clustered across segments, meaning that of the million segments you have, maybe only 1,000 of them have data for a certain artist, and the system does know that and can prune the list of segments to scan accordingly. So that's a scenario where you're not going to get very much overhead at all. Another scenario is if you're filtering on something that you have not clustered by. If you're filtering on something you have not clustered by, then we do have to look at every segment. And in that scenario, there's some more overhead, which is why clustering is so important. And it still is going to work fine if you're filtering by something you're not clustered by. That's actually the scenario we designed for. Like the intent of Druid is that you should be able to filter on anything you want. That's why we have these bitmap indexes and everything. But there will be somewhat more overhead if it's something you're not clustering by.
Okay, awesome. Aaron. I've asked him to unmute. There you go.
There you go. I'm unmuted. Yeah. So, I pretty much wrote it in the question there, but on, dare I say, a larger cluster, if you have that moment where, like, you know what, we really should have done this differently from the get-go, in terms of, very commonly used columns. Is there anything more efficient than going back and just in chunks doing re-indexing jobs, doing the hash-based partitioning?
No, that's the best thing I know of too. I think that if you have a ton of data loaded, if you have an absolute ton of data, and you decided you wanted to partition it differently, then you are going to need to go through and reprocess everything. I think that one of the nice things about Druid is that it does have this goes back to that space we occupy on the storage compute aggregation spectrum. One of the nice things about the space we occupy is that you can scale up the cluster temporarily to do and re-indexing like that really rapidly, and then scale it back down, and that works fine.
Oh, are you talking about in terms of like the indexers?
Yeah, you can add
okay,
a ton
gotcha.
of them temporarily. If you're in a public cloud environment where it's easy to do that, then you can add a ton of those temporarily, do the job, and then you can turn them all off, and it'll be okay because the stuff is going to be in deep storage and will get loaded by other servers.
Gotcha. Yeah, thanks.
All right, next question is Bali.
Yeah, hi. Are there any plans to support high precision arithmetics or aggregations on Druid?
Let's see, high precision arithmetic. You mean like sort of SQL style fixed decimal
Point
stuff?
decimals.
Yeah, the fixed decimal ones, where the precision is of utmost importance. Like you cannot be off by like a digit or so.
Yeah, it's hard to talk about plans in an open source project because that's not really how Apache collaboration works. But there are certainly people talking about it. If you go on the GitHub Apache/Druid and search for decimal types, you'll see some active conversations. So it's something that's certainly being talked about.
Okay, great. I'll follow up there. Thank you.
Floppy disk. This might end badly. If you're a real person, ask your question.
Yeah. So, maybe your last answer kind of touched on this too, but I'm just wondering, are you guys thinking about the Apache Arrow project at all and how kind of some of its aims might play with what y'all are trying to do at Druid and kind of future directions of things?
Funny you should ask. Yes, we are thinking about it and talking about it. Apache Arrow is very interesting. It's of course similar to the Druid segment format in some ways and different in other ways. I think the Druid segment format is a better fit for what we use it for, which is the thing, long-term storage. The Arrow folks have a page on their site about Arrow versus Parquet and the differences between them, and a lot of that applies to Arrow versus the Druid segment format as well. One being Arrow being designed for 100% memory, and then Parquet being designed for long-term archival storage and disk. And the Druid segment format's kind of a blend between them. It's something that is at home on disk, but also is at home in memory, well, anyway, there's that. I think as to where Arrow could be especially interesting and where we're actually thinking about incorporating Arrow into Druid potentially is for transferring data between servers. I think that for something that you're going to read a ton of times and have on disk memory maps, Arrow is maybe not the best choice. But for data that's generated once and then going to be transferred to another server and then read once, it seems to be a really good choice and have less overhead on the write side than the Druid segment format does. Druid segment, because of all the compressions they're doing, reading is quite fast, but the writing is fairly slow. So we push a lot of work to the right side, and with these with transient data that goes between servers, you don't want to do that. You want both to. You kind of want to. You're willing to sacrifice some footprint for having really high speed on the write and read side, and Arrow's good at that. So it might make sense to blend them together. I don't know if that answers your question, but
it does. Thank you.
Okay, good.
All right. So next question is Steve Moy from the Steve Moy Foundation for Keeping It Real.
Hi. Since this is implemented in Java, I'm very interested in if there's an experimentation running on the Amazon Graviton 2 instance where it has excellent memory bandwidth. So I'm kind of interested on that.
I don't know of anyone that's done that, but it would be cool. If you do it, give us a holler.
Okay, so Hamid, do you want to ask your questions you had at the beginning?
Okay, so any comparison with what Druid at Cloudera and also comparison with ClickHouse?
Yeah, so the Druid at Cloudera is relatively similar to Apache Druid. I'm not sure, by the way, I'm not sure if you're asking about the difference between Imply and Cloudera or Apache and Cloudera, because I guess I could represent either one, but none of of the three, I don't think any of them are incredibly far from the others. The differences are at this point relatively modest. So I think that's how I'd answer that question. Imply ones tend to be a bit more up to date than the Cloudera ones. I think the Cloudera one is somewhat older, but other than being older, I don't think it's really diverged terribly much. And then with ClickHouse, ClickHouse is also cool. ClickHouse is a columnar data system that's pretty neat. I think that as it relates to how individual queries get processed and the data formats, it's actually Druid and ClickHouse are pretty similar. As it relates to the distributed system design, they're a little more different. I think that ClickHouse to me has more of a flavor of a strong affinity between data and server. And Druid to me has a weaker affinity, and that comes out in various ways as you think about how to operate a system and scale it and that kind of thing. I feel like the weaker affinity in Druid makes it simpler to think about how to make things elastic, and you sort of just add more processes or kill processes and that kind of stuff. And I think at the same side, I think that the stronger affinity in the ClickHouse world makes it easier to think about how to run a very small setup that might only be 1 or 2 servers. Yeah, that's I think what I would say there.
Okay, thank you.
But a very interesting system.
So for everyone, I posted in the chat, we had the ClickHouse guys come give a talk in May last year for the quarantine talk. So if you're interested in learning more about ClickHouse, you check out there. So I'll finish up. I guess I'll ask my last question. You didn't really get into a discussion of like how the query engine actually is reading this data, especially when you're doing like long scans. Are you guys doing like any like cogen or vectorized execution techniques, or is it just the Java code just sort of doing the standard interpretation that sort of Postgres does? Yeah, so we're doing vectorized queries. I guess I didn't mention it much because it seems like table stakes these days for an analytics database, but we are doing it. We are not doing cogen today unless you count what the JVM itself does, which I guess you could think of hotspots JIT as a sort of cogen. But we haven't implemented anything on our side explicitly in the cogen realm. Got it. Okay. Hamid is asking if you guys are doing joins, but I think you've already said at the beginning you guys do support joins. Yeah, we do support joins. We don't support every kind of I guess shape of join you can think of. So the heritage of Druid is to be sort of on this fast analytics side, powering interactive apps, that kind of stuff. And historically, fact-to-fact joins have not been super important. And so we don't support like a shuffle join or a sort merge join. We support hash joins and broadcast joins. I think at some point we will add support for all that kind of stuff, because I feel like the natural evolution of every database these days is to support everything as you get more and more users. But it's also important to, in your journey towards supporting everything, remember what you actually want to be really good at, and what we want to be good at is this interactive app stuff. And the broker, that's all like custom, or sort of not custom, but like that's Druid code. It's not like you're relying on Calcite or something like that, right? Like you guys wrote your own query optimizer? So good question. The fan out stuff is 100% Druid. The SQL stuff is using Calcite for the optimizer core and for the parser. And then on the Druid side, we like the code that we have integrates with Calcite to basically like teach Calcite how to generate native Druid queries is pretty big. So Calcite's really nice in that it's got a very, very extensible optimizer. And it's a great project, and we are making a lot of use of a lot of its features in order to have its optimizer generate query plans that make sense for Druid. Yeah, so a bunch of people told us they only use Calcite for SQL parsing. It sounds like you're using it for all, like for the parsing and the planning. Other than the fan piece. Okay, awesome. All right, guys. So with that, we are done. Again, Gian, thank you for doing this. Appreciate you being here. Next week we're having it's HarperDB. Double check if I'm correct. Yes. No, wrong. Adam Kolotsky from CouchDB from IBM. He's gonna come talk about CouchDB. And then after that, on March 15th, that'll be HarperDB. So again, same Zoom channel, same Zoom time. Okay, Gian, thank you so much for doing this. Everyone, stay safe, and hopefully everyone start getting vaccinated. Okay. All right. Thanks. Take care, guys. Yep. Bye.